Hey everyone, welcome back to my channel. It's a beautiful afternoon here, so I am just enjoying my iced coffee on my balcony, and we are going to finally finish up those set identity rules, do a couple of practice problems, and then we'll be done. So let's get started.
Okay, so say we have our two sets, A and B, and say we have their intersection. Now, my question is, how do we get from the intersection of A and B, let me write this down, how do we get from the intersection of A and B to A? So what do we do to the intersection of A and B to get to A? So we just need to find a way to get to the whole blue circle, so the whole A circle. So all we need to do is take the total area of this almond shape with the rest of the circle. So all we need to do is take the union of the almond shape, A intersect B, with A, and then we get A. So A intersect B union A equals A. Okay, let's look at the problem from the other angle. So say we started with the union of those two sets. So we start with A union B. What do we have to do? What do we have to do to A union B in order to get A? Well, let's look at it. So all we need to do is find the area that overlaps with A union B to get A. So all we need to do is just eliminate this region here, right? So all we did was we took the overlapping region of that union with A. So all we did was we intersected it with A. So A union B intersected with A equals A. So these are what's called the absorption rules. So if we have the intersection of A and B, if we take the union with A, we get A. If we have the union of A and B and we intersect it with A, we get A. So this is how to go from the union or intersection of A and B to A. Okay, all we have left are the pretty simple ones, so let's have a look. Okay, so we want to know what the complement of the universe is. So we know what the universe is. It's the set of things in the universe such that something true, something that's always true. So like 1 + 1 = 2, for example. Right? Because we test every item to see if this condition is true. And in this case, it's always true, because 1 + 1 = 2 is always true. So everything goes in this set. So this is the set of everything, the universe. So what's the complement of the universe? Well, it's anything that's not in this set, right? It's the set of things in the universe such that X is not in the universe. Well, what would that be? It would be something like the set of things in the universe such that 1 + 1 = 3. Something that's false. So anything that's full. So everything we test, whether it goes in this set or not, whether it meets this condition, everything fails because the condition is always false. So nothing goes in this set. So it is the empty set. And then the second part of the rule is that the complement of the empty set is just the universe. So we can kind of see this is just the reverse of this inference. So the complement of the empty set will be anything in the universe such that X is not in the empty set. So now we know that the empty set is nothing. The empty set has nothing in it. So everything isn't in the empty set. So this is always true. So the complement of the empty set is the universe, and the complement of the universe is the empty set. Okay, let's look at the next one. The universal bound rules. Okay, so this is just saying that A union universe is the universe, and A intersect empty set is the empty set. Now this is pretty intuitive. So if we have A as some set in the universe, the total area of A and the universe will be everything in the universe. So the union of A and the universe is the universe. The intersection of A and the empty set, the set of things that are in both A and the empty set. Well, we know that nothing is in the empty set, so nothing could possibly meet that condition. So the intersection of A and the empty set is the empty set. That one's pretty intuitive. Okay, so let's look at the last one. Our very, very last set identity rule, the Idempotent Rules. Maybe that's not how you pronounce it. How do you pronounce it?
Idempotent or
Okay.
idempotent.
Oh, okay. So it's either way. Idempotent or idempotent. Okay. So idempotent rules. So idempotent means it can be the same. Okay, so all this is saying is the union of A and A is A, and the intersection of A and A is A. Now it's pretty straightforward, right? So if we have a set A, the union of A and A is the set of things that are in either A or A. Well, that's just A. The intersection of A and A are the set of things that are in A and in A. Well, that's just A as well. So if we take the union of something with itself or the intersection of something with itself, we just get that thing on the other side of the equal sign. So those are the last and final set identity rules. Yeah, these ones aren't too complicated, pretty easy to remember, pretty straightforward, pretty intuitive.
So that is it for all of our set identity rules. So we actually went through 12 different rules over this video and the last two. So if you need a cheat sheet, screenshot this. I'm going to put all 12 on the screen now. Okay, so let's do a couple of practice problems before we go offline, and yeah, let's get started.
Okay, let's try another one. So this is asking us to prove this subset relation. So A union B intersects C is a subset of A union B intersects C. Okay, so how do we do this? So how do we prove a subset relation? So to prove a subset relation, we just need to say that if any element is in this set, whatever the element is, it's also in this set. So being in this set on the left means that you are automatically an element of the set on the right. Okay, let's see how it works. Okay, so I don't actually know what the answer is yet, so let's just play around and see what happens. So let's start with the commutative rule to put the C on the other side. So C intersect A union B. Okay, and now we'll do distributive. So we'll put C in the scope of the union. So C intersect A union C intersect B. Okay, now we've already kind of got something that looks like this on the right here. So we're on, well, let's use the commutative rule again to swap the positions of these. Let's use it twice. So A intersect C union B intersect C. Okay, so we've got a term here that looks very much like the term on the right here. So I think we're pretty close. Okay, well, I think we can already make an argument that this is a subset of this set, because if we're in this set, we're either in B intersects C or A intersects C, right? There are two options. If we're in this set, we're in either A intersects C or B intersects C. Now, if we're in B intersects C, we're already a member of this set as well, right? Because if we're in B intersects C, then we're within the union described by the set on the right here. Okay, the other option is if we're in A intersects C. If we are in A intersects C, then we're also in A, right? Because A intersects C is a subset of A. Any intersection is a subset of both sets, right? So the intersection of A and C is a subset of A. Because if this is A, this is C, this is the intersection is a subset of A. It's also a subset of C. So for any X in A union B intersect C, X is in B intersects C, or X is in A intersects C. So if X is in B intersects C, it's in this set, so it's already in this union. If X is in A intersects C, then it's also in A, right? By this law here. So it will be in this side of the union, okay? Let's draw a diagram, I think it'll make it clearer. Okay, so A union B intersects C. So A union B is this figure 8 area here, but we only want the area intersecting C, so it's that area there, is a subset of, so this area needs to be wholly contained within this area. Let's do that area in yellow. Okay, so B intersects C is this area, union A. Okay, so our original area in pink here is wholly contained within the area on the right, so it is a subset. Okay, last one. So this is asking us, prove that for all A and B, if A is a subset of B, so if A is wholly contained within B, then B's complement is wholly contained within A's complement. Okay, so if we think of sets like concentric circles, then I think this becomes pretty clear if all we do is just draw a diagram. So let's say we have B, which is this big circle. This is B. And we also have A. We also have A, which is this smaller circle. Okay, I think this should be a little clearer. So here we have a situation where A is a subset of B, right? So A is a subset of B, it's a proper subset in this case. Then B's complement is a subset of A's complement. Okay, so B's complement, B's complement is the area outside of B, so this yellow area. And we can see that B's complement is wholly contained within A's complement, because A's complement includes that yellow area. So A's complement we're doing in blue now. A's complement contains this area because that's outside of A as well, but it also contains this area, this donut shape area here. So we can see that B's complement is the area outside of B, and that is wholly contained within the area outside of A. So what does this tell us? That if A is a subset of B, if we have this concentric circle type situation here, then their complements are in the reverse subset configuration. So B's complement is a subset of A's complement. This is a special property of the complement symbol, that it flips the direction of the subset relation, right? So A subset B, if we have A subset B, then if we put complements on both sides, A complement, B complement, the subset goes in the other direction.
Okay, that's it. So thank you so much for watching. Please remember, like and subscribe, hit the notification bell, and join me next time for some more set theory. See you later. Bye.